Hi, welcome to my medium ISP, the 32x32 RGB matrix. So the matrix itself here consists of 1024 RGB LEDs in a square arrangement. While this version of the matrix was much too complex for the auto router to work, it would have had a camera attached and it would display the feed from the camera live. So now that we understand what the matrix does, let's get into how it works. The principle upon which the matrix operates is demultiplexing. So demultiplexers can be thought of as selectors. They pass a singular input line to one of several output lines based on the binary count. So if all the select pins were low, for example, then it would pass the input to Q0. If all were high, it would pass the input to Q7. The next thing to note is that each RGB LED contains 3 standard LEDs, one red, one green, and one blue, which gives us a total of 3,072 total LEDs. So for this reason, the matrix uses a 1 to 3,072 demultiplexer. This means that each LED in the matrix has its own output pin on the demultiplexer. So the LEDs are wired sequentially to the demultiplexer outputs in rows. The first LED would be wired to Q0, then Q1, Q2, Q3, all the way up to Q31. And then it loops back around. So this would go to Q32, 33, 34, and it goes across in rows and then down in columns until the very last LED, which would be Q3071. So the select pins of the demultiplexer are run by a 12-bit counter that's clocked at 20 megahertz, and that's fed directly into the select pins. So what that means is the demultiplexer pins are constantly being changed. It's always going from 0 to 3071 really quickly, which essentially means that the demultiplexer is always scanning across rapidly at around 20 megahertz. So the penultimate consideration to this project, I'll set this aside for now, is what drives the input of the demultiplexer. And that is something called a variable constant current LED driver. So this is a circuit that provides a fixed amount of current on the output, which is here, based on a given voltage. So it basically maps a voltage to a current between an upper and a lower limit. So the way that it works is there's this drive transistor and there's this feedback transistor. So the feedback transistor is measuring the voltage across this resistor called R-sense. And then based on the voltage across the resistor, it's going to sink a certain amount of current from the base of the drive transistor. So if the current is too high, then it'll measure a larger voltage drop across R-sense and sink more current away from the base of the drive transistor until the current is stabilized. And so as you control the control voltage, as you increase it, more current is going to flow through the whole system. Now, since a forward current versus luminous intensity or brightness graph would look something like this, we know that luminous intensity is approximately proportional to forward current. So by changing the current, we're basically directly changing the brightness. Now the final thing to note is that if we attach an R2R ladder to the control voltage, then we can essentially convert a binary number to a voltage, or in other words, we can convert a binary number directly into a brightness of an LED in a predictable manner. Now the last consideration is where the brightness data comes from. And for that, the matrix uses a RAM chip. So for this, the brightness of each LED is stored in the chip in the order that it's going to be accessed. So in address 0, when all the address pins have a 0, the brightness for LED 1 is stored. Then in address 2, the brightness for LED 2 is stored, and so on, all the way up to LED 3071. Since the brightnesses are stored as binary values in the chip, it makes it quite easy to display. The output of the RAM chip goes directly to the R2R ladder in the constant current source. Also, the counter is synchronized with the RAM address pins. So that guarantees that the value being read from in memory is going to line up with the desired LED on the demultiplexer. So if the counter outputted all zeros, that would mean that LED 0 is selected. So the input, which is coming from the constant current LED driver, is mapped directly to LED 0, which is there, and at the same time, the address being read from in RAM is address 0, which, as we know from earlier, stores the brightness value for LED 0. Now, since the output of the RAM chip is mapped directly to the constant current LED driver. That's going to put the brightness for LED 0 onto the R2R ladder of the variable current driver, which is going to set up the correct LED with the correct brightness. And then it cycles through in rows and columns as mentioned earlier, and that's how it displays an image on the matrix. Finally, there's actually 2 RAM chips, and that's how video is accomplished. Basically, it acts as what's called a double buffer, which means while one RAM chip is being read from, a second RAM chip is being written to. And this changes every time the frame changes, and then they swap using multiplexers. So the result is that the live feed from the camera is put directly onto the matrix. Thank you so much for watching this video. I hope you enjoyed this ISP presentation.